oxygen, so your dipoles go towards oxygen because it's got the biggest pull. In order for a structure to be polar, it must be covalently bonded and have dipoles. If you don't have dipoles, you're not polar at all, okay? Must have dipoles. A structure is polar overall if a net dipole results. So these dipoles are going to cancel. There's no net dipole. Therefore, the structure is nonpolar. So if when you add your vectors, they cancel, you're nonpolar. You always add the head of a vector to the tail of the next vector. All right. What if we have this? What shape is this? Linear. So now we've got X and Y as our atoms. They don't have the same electronegativity. So what do you think? Are the dipoles going to cancel? They're not going to cancel. So net dipole, therefore polar. So on this one, the net dipole is going to be towards Y because it's bigger. Okay, so you've got a net dipole. That's a very bad arrow. Okay, so net dipole. Trig planar. So all these bond angles are 120. Let's say A is more electronegative. What shape is this? You have to answer a question before.
What shape is that?
Yeah, what shape is that?
Am I allowed to look at my finger?
No. What shape does that make?
A square. A triangle?
A triangle. Are these in the same plane?
Yeah.
So it's trigonal planar, because it's in the plane of the paper. Okay, now ask a question.
In the top one there, why, how do you know that the Y is bigger?
Because I told you.
Oh.
This time
It's like the one's longer than the other? So
yes,
like,
so that's big, that's a bigger dipole.
Oh,
Okay, so that's a bigger dipole.
The green one just to show that it's that way is more polar.
That means if I add these two together, this is only gonna cancel this much. So the net result is gonna be in that direction. So it's like this. I've got,
So would you actually draw it like that or no?
yeah, you can draw it like that.
So you add the net dipole thing to it?
Yep. Yep. So if I go this way first, then, because you're doing head to tail, you're now going back this way. Did I finish at the exact location that I started? No. So your net dipole goes, the tail is from the start to where you finish. Okay? That's how you add your vectors. Now this one is nice because it's actually symmetrical. When you have a symmetrical structure, like triplanar, linear, if you cut it down the middle and it's the same on both sides, it's going, all your dipoles are going to cancel. So this one, you have a dipole coming this way, and you've got a dipole going this way, and then you've got a dipole going that way. So you are back where you started, so there's no net dipole. It's exactly it. It's a resultant vector. So no net dipole, therefore non-polar. The dipoles cancel. So you're asking me if you put these on?
Yeah, no, like, yeah, like if you're on a test, which like, and you say like do the polar or whatever, do you like write them still?
You should still put them on.
And then just say it's not polar?
And then just say no net dipole.
Okay,
Yeah. Because otherwise you don't have any work to show,
yeah.
right? So this has a net dipole, so it's polar. Yeah?
Does it matter like how you go about like the order of the
No.
videos?
It doesn't matter at all as long as you use all three.
Okay, so even if you went like the blue, red, blue, it's still like the same?
So which one do you want to start with? We'll number them. 1, 2, and 3.
You did 2, 3.
So 2, 3, 1. It's not going to matter the order as long as you use all three.
So if they cancel, do you still write the dipoles down? Like
You
on the
mean
test or
these?
something? No, like on like the other one that you did. Like they
These?
cancel. Like the ones that actually cancel. Like those don't cancel. Like if it's not
Are you
just-
asking me if you put these on or these
No,
on?
no, no, like the question before.
The question
Like one
before.
where like there's no net dipole.
Okay. This one. This one's a little harder to show because now we're getting three-dimensional, right? It's coming out of the page, it's going behind the page. What would happen if I had one going down and back and one going down and front? They would cancel? Do you guys agree?
They just end up in the same place they started.
If I go down this way and then I add down this way, would I not be further down?
But like, oh, you're not talking about like this way and then back this way?
Yeah, no, no. Because these guys go down, right?
Yeah.
I'm going to just save you some trouble here. Tetrahedral, equal dipoles, symmetrical, no net dipole. Okay, tetrahedral. Symmetrical, no net dipole. It's really hard for you to draw the dipoles for this one. Okay? So if it's tetrahedral, like CF4, CH4, symmetrical, no net dipole. However, this is not symmetrical. Therefore, net dipole polar. Okay? This goes back to a rule that I taught you last year. And you guys had to remember two groups of chemicals that were always nonpolar, everything else was polar. And you're all looking at me like, okay, so what was it? Because we don't remember. Am I right?
Yes.
Page 85, Table 3, Grade 11 textbook. So, diatomic elements. Do you remember what they are? Hofbrinkel.
Sauce. The mid.
Hofbrinkel.
Oh, I remember this now.
Okay, yeah. Diatomic elements, not diatomic compounds, because you can have diatomic compounds. HBr, HCl, ClBr. If you have two elements that are not the same, it's still diatomic, but it's not an element, because they're not the same. Okay, so diatomic elements, difference in electronegativity is 0. Therefore, they are polar or nonpolar? Difference in electronegativity is 0, nonpolar. If you don't have dipoles, you can't be polar. Okay, the other one, carbon bonded to one other element, and there's an even number of that element, nonpolar. And this is why, right? If it's tetrahedral or linear, then you've got dipoles that will cancel, or no dipoles at all. So carbon bonded to one other element, so we're talking like an X, and there's an even number, like 2, 4, right?
Carbon bonded to anything, that's an even number?
But only one anything.
Okay, so it could be like C,
CPO. If there was something CPO, would that be polar or nonpolar?
add it to.
No, that's polonium.
Oh, you wanted polonium, did you? Well, then you're getting into metals.
That's true.
So that's not covalent. But let's say it was something like this. Would this be polar or nonpolar? Polar. Because there's 3 elements. Okay. How about this? Polar or nonpolar? Nonpolar. How about this? Nonpolar. How about this? Nonpolar. 1 element, even number. How about this? Polar. CH3Cl. Polar. Because there's 3 elements. Okay? So maybe we need to move it. How about ammonia?
Hydrogen bond.
It does. What else does it have?
Covalent.
Oh, just leave it there. That'll be fine. Thanks, Matt. Say that again? It has all 3. So therefore, I think we can be pretty assured it's in the right place. It's got 3 types of intermolecular forces. So the forces of attraction holding the molecules together are stronger, therefore, shall I say that again? The forces of attraction holding the molecules together are strong, therefore, a lot of thermal energy, the scientific way of saying heat, is required to overcome those forces of attraction. So the forces of attraction are strong, therefore you need more thermal energy to overcome those forces of attraction. We do not remove any electrons. We do not break apart the molecule. We break the molecules apart from each other into individual discrete molecules. We do not break covalent bonds. H2O liquid is exactly the same as H2O steam. Gas, right? It's the same, H2O. 2 hydrogens bonded to an oxygen, just there's more space between them. Okay, lithium fluoride, what does it have? It's ionic. It has no intermolecular forces. All ionic compounds are solids, which tells you very strong forces of attraction in the structure. Butene, or but-2-ene is the new way. What does that make the one below it? 1-butene. Old school, 1-butene. New way of naming. I, for a million years, have done it the old school way. Your new textbook, the new IUPAC rules, are the second way. I'll take either, but when you get to university, it depends on the age of your professor. Really. Okay?
What do you say the new rule is, like IUPAC or something?
The IUPAC, yeah, they've changed it so that the number is within the name.
Oh.
Okay, so is that it? Any more? Yeah.
2-methyl 1-propene.
What about this one? Partic. Do you like this one?
Isn't that the exact same as
Because don't you have to start numbering it because it's the exact same?
As which one?
the one?
As the one on top?
No,
Same as the fuse one.
These are the same, right?
You start numbering closest to the.
Closest to the double bond. Yay! Okay, so they're the same. So Nikita said 2-methyl but-1-ene, or 2-methyl but-1-butene. So you always have to say where your side groups are, and you have to say where the double bond is. Now technically, that would be 2-methyl propene. There is only one place for the double bond, so you don't have to put it in. However, I'm going to strongly suggest to you at this point, you always put the number in so that you never forget to put it in when you need to put it in. Okay? I will mark it correct either way for this one. All right, any others? Or are we done?
Wait, so that one is also but-20, right?
It's not but. Longest carbon chain there is how many?
Oh,
Prop.
oh, so it's propane.
So it's 2-methyl. Propene. Okay? Can you tell me if there's any other isomer? Some of you that have moved ahead would know the answer. Cyclobutene. If you come back to this structure,
Cyclobutane.
that's actually a geometric isomer. Because each carbon for the double bond is bonded to two different groups. It's bonded to an H and it's bonded to a methyl group. This one does not have a geometric isomer because the first carbon's bonded to the same two atoms. So you can have geometric isomers if the carbons at the double bond are each bonded to two different things. This one is bonded to two H's, so it's not a geometric isomer. This is bonded to an H and a methyl. This is an H and a methyl. So this one has a geometric isomer. So technically, there's another isomer.
What about the?
We're not going to get into enantiomers. You might in biology. Okay, so if you take a look at this, you've got cis and trans. So these are both but-2enes.
So these are still isomers.
They're still isomers, so this is adding an isomer. So here, the hydrogens are on the same side. It's a cis isomer, cis same. Here, they're on opposite sides. This is trans. But-2ene. So these are the structure, these are the general formulas right here for an alkane, an alkene, an alkyne.
Alkane, alkene, alkyne.
Cane, keen, kind. Aye.
Each time you add another bond between two carbons, you're removing two H's, right? Does that make sense? Okay, I won't explain it then. So what's what? What's the first one? Alkane? Alkene or alkyne? Uma? Don't guess, I've given you a formula. What's double 56? Okay, maybe you need a calculator. What's double 56?
The first one.
The first one. 112, you mean?
Also it'd be CnH2n.
Yeah, so that is an alkene. What about the next one? Also an alkene. What about the last one? An alkyne, because it's short too. Anytime you have to make a multiple bond, you're removing 2 electrons,
The last one's.
2 hydrogens.
The last one's alkyne. This is the first one.
It's an alkyne, this one.
That's an alkyne.
I didn't draw any alkanes
What's this?
today.
Anytime, or like right now?
It's supposed to be in class.
I put it in the bucket, actually.
Just so we be, I didn't finish question 5 because of the typo, so can I bring it to you in MSIP?
Oh, because the typo that I fixed yesterday on Schoology?
I honestly was gonna check it when I saw you posted it, but I forgot. I got doing something.
Get it in.
Okay.
What would this be called when it's different?
That's just one butene.
No, for geometric isomer on the opposite side is the same side of hydrogen.
That's cis, right? That would be cis 2 butene. The hydrogens are on the same side.
I mean, like for geometric isomer, wasn't there another one?
Cis and trans for that one. This doesn't have, does not have a geometric isomer.
So just not a geometric isomer. Is there a
It's
name?
just a structural isomer.
So that's what
Okay?
How's it going?
It's going, you. Line diagrams are better. When you have cyclic compounds, they're less messy. So this would be cyclo, bute 4. Are there any double bonds? Do you see any double lines? Do you see any triple lines?
No.
So then it's an ane. It's saturated. Each carbon's bonded to 4 atoms. That would be an isomer of this, C4H8.
Cyclone.
Next video.
It's the next video.
So we have to watch the next video too then?
If I was going to give you a question,
So would this be, so is there a possibility,
You have to watch all the way up to alcohol to have that.
yeah,
is there a possibility
esters,
cyclo.
esters.
of cyclo?
If I give you a isomer question. Did I get into cis and trans?
No?
No.
Oh, yeah, you did.
First video, I think, didn't I? So if you come back to this one,